Hi everyone, and welcome back to another episode of Science. In this episode, I want to teach you all about velocity and specifically how to calculate velocity. So let's get started. Velocity is a speed in a given direction or rate of change of displacement. So velocity is what's called a vector quantity. It will give you a speed and a direction, two pieces of information. Velocity will give you a direction and it will give you a magnitude, for example, speed. And this is called a vector quantity. Vector quantity. Now there's a formula we can use to calculate velocity. So it's the change in displacement divided by the time it takes to travel. Or it's the final position, the final distance, take away the initial distance, or displacement, I should say. The final displacement, take away the initial displacement. Divided by the final time, take away the initial time. And your directional velocity will equal the direction of overall displacement. And I'll show you an example of what this equation looks like when you're actually calculating a question. So let's begin. David is in a 100-meter race and covers the distance in 11.5 seconds. What is his displacement? Well, assuming he starts from the starting line, which will be 0, and then he runs 100 meters and he finishes at the finish line, then his displacement is going to be 100 meters. And if David was to walk back to the starting line, then his displacement would return to 0 meters. But in this question, David has just sprinted from the starting line to the finish line, which is 100 meters away, and so therefore David's displacement will be 100 meters. Now what is his velocity? So let's use our equation from the last slide. So the final position, take away the initial position, divided by final time, take away the initial time. So his final position, his final distance, his final displacement is 100 meters, take away 0, which is what he started from, divided by 11.5 seconds, which is his final time, take away his initial time, which was 0. And so this equation just ends up being 100 meters divided by 11.5 seconds. And if you just punch that into your calculator, 100 divided by 11.5 equals. So this gives us a velocity of 8, and we can round it up to 8.7 meters per second, and we can say forward. They've sprinted forward. Like so. So David's velocity is 8.7 meters per second forwards. Now the calculation has worked because our units were matching. I've got 100 meters and seconds, and so meters and seconds match. Keep in mind that if the time unit was in hours or if this was in kilometers, you'd have to do a conversion to make the units match. Let's do a more complex example. Tanya walks to her friend Stacy's house 500 meters away north. It takes her 2 minutes. They hang out for 8 minutes. Their friend Ava invites them both over to relax by the pool. Ava lives 750 meters south of Stacy's house. It takes them 5 minutes to reach Ava's house. So there are a lot of pieces of information for this particular question. The best thing I would recommend is to actually draw out the movement. So let's start with Tanya. Tanya starts here. Okay, that's her starting position. And I can just write Tanya here. That's where Tanya starts, and then she walks to her friend Stacy's house 500 meters away north. So let's draw this arrow here, and this is 500 meters away north. Now, if you've got a writing book next to you or a piece of paper and a pen, definitely do it with me because you could certainly do it a lot neater than what I can do with my mouse. The journey takes her 2 minutes. I've got 8 minutes and 5 minutes. Now we've got minutes and meters, which is not ideal. We want meters and seconds. So let's go ahead and convert this into minutes. 2 minutes equals 120 seconds. 2 times 60. And 60 seconds is 1 minute. So 2 minutes is 120 seconds. 8 minutes, if we times 8 by 60, gives us 480 seconds. And this 5 minutes here I want to convert as well. So 5 times 60 gives me 300 seconds. So now I've converted all my minutes into seconds, which matches the meters that I'm using for the distances. So it takes Tanya 120 seconds to walk 500 meters to Stacy's house. Now they hang out here for 8 minutes, 480 seconds. They stay here. We'll just leave that for now. Then their friend Ava invites them both over to relax by the pool. Ava lives 750 meters south of Stacy's house, which is here. So now they've got to travel the 500 meters back in the same direction, plus another 250 meters south, because they're going 750 meters from Stacy's house here. So 750 from Stacy's, and here you arrive to Ava's house here. So this journey is 750 meters, and that takes 300 seconds. 300 seconds. Okay, so now we've drawn it out and we've got all the pieces of information that we need. Let's start answering the questions. What is Tanya's distance traveled? Now, distance is the total number of meters that she has traveled. So we've got 500 here and 750 down. If you go 500 plus 750, that will give you 1,250 meters. Displacement. Now, displacement is her straight line distance from her starting position to the ending position. And in this case, the difference between Tanya's starting position and ending position is 250 meters south. She's ended up 250 meters south of her starting position at Ava's house down here. Now, average speed in meters per second for the whole time. See if you can work this out. Pause the video, and once you think you've got an answer, unpause and check with me. Okay, assuming you've paused the video, average speed in meters per second for the whole time. Now, average speed is d over t, distance over time. So I've got my distance here, 1,250. The question is, what is my whole time? Well, I've got 120 seconds here, 480 seconds here, and 300 seconds here. So I need to add up all of this time. Keeping in mind, this time here is the time they spent hanging out. But because the question is asking us for the whole time, we want to include the time that they used to hang out at Stacy's house here. So let's add up all the times together to get our total. 120 plus 480 plus 300 equals 900 total seconds. So my total distance is 1,250 divided by 900 seconds. That's going to give me 1,250 divided by 900. That gives me an average speed of 1.3, I'll say 39 meters per second. And because it's just speed, we don't need to include a direction. So 1.39 meters per second. Now you can also calculate this just for the time they were moving. All you have to do is not include this 480 seconds. So if I was to go 120 plus 300, that would give me 420 seconds in total here. And if I did the calculation again, 1,250 divided by 420 seconds, the average speed while they are moving only comes to 2.98 meters per second while they are moving only. But if we're incorporating the whole time, that includes the time they hung out at Stacy's house here. Final question. Average velocity in meters per second for the whole time once again. So pause the video here, go back to the formula and see if you can calculate the average velocity in meters per second for the whole time. Okay, assuming you've paused the video, let's have a look at the formula here. So my average velocity equals my final displacement take away my initial displacement divided by my final time take away my initial time. So coming back to this question here, my final displacement was, this is where Tanya had started, and her final displacement ended up being 250 meters, 250 meters south of where she was. And so my final displacement, 250, take away my initial, which was 0. So that gives me a displacement of 250 divided by the whole time. And our whole time was 900 seconds. So this time if I go 250 divided by 900, that gives me a velocity of 0.28 meters per second, and you have to include south in that as well. 0.28 meters per second south. So that is her velocity. Okay, hopefully you were able to calculate some of these practice questions. If not, rewatch the video and have another go at it. Let's continue moving forwards and have a look at a couple of graphs. So this one here, got a displacement time graph. Let's have a look at this first graph here. I'll just assume there's been no units given to these numbers, so I'll just give them a unit. I'll make this one meters and I'll make this one seconds. So for this displacement time graph, sometimes called a position time graph, in the first second I've moved 1 meter, and between 1 and 2 seconds I've stayed stationary, indicated by the straight line, and in the final, between the 2 and 3 second, the final second of the graph, the object has moved back to its original position. So what is the final displacement of this object? Well, the final displacement would be 0 meters because they've come back to where they've started. What is the total distance traveled? Well, this will be a different story. The total distance traveled is, well, you go 1 meter in the first second, then you stay there for another second, and then you come back another meter in the last second. So your total distance traveled will be 1 plus 1 here. So total distance is 2 meters. Let's have a look at this graph here, another displacement in meters and time in seconds graph here. In this graph, in the first 5 seconds, the object has traveled 4 meters, then it has returned to its original position, and it has gone beyond its original position and gone into a negative direction and then stayed there stationary. So what is the final displacement for this object? Well, the final displacement, came back to where it started and then it went backwards for another negative 4 meters. If you line it up here, so the final displacement is negative 4 meters for this graph. What is the total distance traveled? Well, we've got 4 meters here, plus another 4 meters to come back, plus another 4 meters in the negative direction. So the total distance traveled is 12 meters. Let's keep moving forward. Displacement time graphs. Okay, so here on your piece of paper, see if you can draw a rough graph. You don't have to include units of what this question looks like. Draw a displacement time graph without units or values for a swimmer who completes a 100-meter swim in a 50-meter pool. Pause the video here and have a go. Okay, assuming you've paused the video, your graph should look like that, okay, with your meters here and your time here. You don't need to incorporate units, but we know that it's a 50 meter pool, so you could put 50 meters up here. The swimmer starts at the bottom here, and with consistent speed, the swimmer swims to the end of the 50-meter pool, takes a second or two to do a little tumble turn, and then the swimmer comes back to the starting position to finish his or her race. So your displacement time graph for this swimmer should look something like this. Let's have a go at a velocity time graph this time. So this one might be a little bit trickier. In fact, this is definitely a little bit trickier. Draw a velocity time graph without units or values for a person throwing a ball into the air and catching it after it falls. Pause the video here and have a go. Assuming you've paused the video, your graph for this one should look something like this. Like so. Now, the second the ball leaves your hand as you throw it up, the ball is actually at its maximum velocity. That's the fastest moment for the ball. And as the ball travels upwards, gravity is always slowing it down. It slows it down, slows it down, slows it down until it reaches the top of its height, where it remains stationary for a split second, and then gravity begins to accelerate it back towards your hand in a negative direction. The ball then hits your hand and its velocity comes to a stop. So in this case, the y-axis is velocity and the x-axis is time once again. At the beginning, when you throw the ball up, it's at its maximum velocity. As it goes up into the air, gravity slows it down until it reaches 0. And then gravity accelerates it back towards your hand in a negative value direction until it hits your hand, and then the speed returns to 0, the velocity returns to 0. Okay, from here, you should go ahead and practice on your velocity time goodness booklet that I've given you. Continue with Education Perfect, or you can rewatch this video for another go at it. Thank you for watching this episode of Science, and I'll see you next time in class.